So we just published trends in AI supercomputers, and it's all about trends in AI supercomputers. So like the main
That's
thing
a
we
great
find
title.
is the main thing we find, this probably won't be surprising to anyone, is that you have these compute needs for AI that is growing massively, and like this compute has to come from somewhere, and it's obviously coming from these AI supercomputers. So like clearly the performance of these things just has to increase exponentially, and we find it doubles every 9 months. But the thing that people I think aren't as aware of when they're thinking about their compute needs is like, what does this look like in the physical world? And there's like two things that are like pretty interesting to me. And one thing is that the power needs of these things are just growing exponentially. They're roughly doubling every year. So that like the leading system, which is currently xAI's Colossus supercomputer in Memphis, Tennessee, and that thing needs 300 megawatts of power. To put that into perspective, if you look at a US household, that's like 200,000 US households. And so it's like a small sized city is the equivalent of like a single AI supercomputer today. And we're talking about exponential trends. So like that's going to go up in the future. So that's like what the one thing. And the other thing is the costs are also obviously going up, because if you are just massively increasing these chips, and xAI's Colossus has like 200,000 AI chips, H100s and H200s, then those are like going to cost a ton. So we estimate, and it's kind of hard because we don't know like what kind of discount they got for the chips, but we estimate they paid about $7 billion just for the chips, and like all the, like not just the GPUs, but also the server components and the network switches, etc. And they paid $7 billion for all of that hardware.
So this is just the hardware. It's not the power, not the building around it. It's just the hardware, like the
Yeah.
chips.
It's just the
Seven
hardware though.
billion.
Like if we also like added that on top, that's like substantially more, but the hardware is the biggest chunk. I would estimate like if we add the data center costs with all the cooling components and electricity, that's maybe like another 50 billion, sorry, like another 2 to 3 billion or so. So like maybe it brings it up to 10 billion for the whole project.
Right. So 70% is just going to Nvidia. Or am I
Basically,
simplifying
I
it
mean,
too much?
Nvidia also like has to pay some to get these chips
Yeah.
manufactured, but they charge pretty high margins. So like half of what
Yes.
Nvidia makes is probably margins. So they
Yeah.
get a lot of money.
And the first thing you said was that it doubles every 9 months.
Yes, that's correct.
What is it that's doubling? Just the compute, like the flops that the supercomputer can output, or?
Yeah, exactly. So the flop per second, like that's I like to specify it because sometimes people use flops for like the total compute. So the
Yeah.
performance of the thing is doubling every 9 months. So it means like if 9 months ago you needed say like 10 days to train GPT-4 on this cluster, like now you only need 5 days to train the same system because the performance has doubled. And like on the flip side, it also means like you can train something that's twice as big as GPT-4 in the same time frame, so in 10 days.
Right. And for how long has this trend lasted? Like how long did you go back?
Yeah, so we went back 6 years. We started in 2019. And probably I think that's roughly how long the trend went, because before then people weren't really thinking about scaling AI training runs. So we have like very different trends. And like one really interesting thing that we see in AI supercomputers in our study period is that back in the early 2020s, so like 5 or 6 years ago, the majority of systems were like government procured systems. So like the Department of Energy in the US was like, okay, we want a big supercomputer, so all the researchers can use these resources to like run their simulations and like material science stuff, etc. And then all the big things that we find back in 2019, like 60% of them are owned by governments or academia. And then that drastically changes up until today. And now we're roughly 80% companies and only 20% government. So like the use case of these things has just changed drastically from being used for science to now being industrial machines that power like economically valuable workloads that people want to use every day.
Right. So if you go, like if you just, I don't know, it's not part of the study, but like if you would have gone back further, the doubling per year would be, or the doubling time would be slower because governments are moving slower, and those were the primary holders of the compute, basically.
Yeah, there's two reasons why I would expect them to be slower. So one is like one of the big trends we see is like more investment, just creating, giving companies more money to build larger systems. But the other thing is also that if you look at the trend in AI chips, that trend has been really fast recently because Nvidia had so many incentives to like make better AI chips. And like I'm not sure if we went back like 10 years or so, if the AI chips were also increasing at the same rate. But I haven't looked at this closely. It might also be, I mean, on the other hand, like Moore's law was way stronger like 10 years ago. So maybe like by default chips were getting better. Now Moore's law is slowing down, but Nvidia's like squeezing out a lot of performance just by improving the design a ton. And like the new chip that's coming out this year, the B200, that's like I think 2.5 times better than the H100. So that's like 2 years and they more than doubled the performance of the chip. So like Nvidia is really going strong on the design side. So I'm not sure how that would level out, but definitely in terms of the investment was increasing way more slowly because it was mostly governments. And like they were like, there was kind of like a cute little race because like Japan wanted to have the biggest one, Germany wanted to have the biggest one, China and the US, and they all tried, and there's like the top 500 list, which like everyone was submitting to. And then people were like trying to figure out who has the biggest one. And we don't really see that now. Like, I mean, I guess governments maybe still like are thinking about that, but like now the biggest systems are all industry systems. So like all the governments like can't compete anymore, at least not right now. Maybe if like they poured like billions into these kind of systems, then they could again. But right now they're just not very competitive.
Mm-hmm. Okay. And this trend with doubling every 9 months, has that lasted? Is that basically just if you extrapolate from 6 years ago until now, or has it actually doubled every 9 months and been consistent that way?
Yeah, I mean, this is the average. If you look at the actual biggest system, it looks very different. It's like it's the same system, then there's like a huge jump, then there's like another huge jump, etc. So it's yeah, that's why what we do in the paper is we take the 10 largest systems and then we average between the 10 largest rather than just taking the biggest one, because otherwise it's kind of like not very scientifically sound to just look at the single system. And another thing that might be worth like highlighting here is that we only cover, in my estimate, about 10 to 20% of all chips in these systems. So like roughly 10 to 20% of total performance as of today, as of like March 2025. So we don't know if there are bigger systems that we just miss. For example, I'm pretty sure that when the H100 first came online, like Microsoft, Amazon, Google, all of those, they just like built huge clusters, but didn't always announce them. So we only capture those that these companies actually want to announce. And that's why like it looks like this rather than like a smooth curve where we actually, if we captured all of them, I think it would be way smoother than it is in the paper.